Okay, we're going to get into a new section entitled the central limit theorem. Now, the central limit theorem cannot always be used. So, the first thing we're going to talk about is when it can be used. The central limit theorem. There are two cases to consider. Normally distributed and not normally distributed. If it's normally distributed, you can use the central limit theorem for any sample size, for any sample size n. If it's not normally distributed, you can use the central limit theorem if the sample size n is more than 30. So if you're not told that the data is normally distributed, you can still use the central limit theorem, but n must be greater than 30. Okay, having said that, let's do some central limit theorem problems. Now, central limit theorem problems, in my mind, is exactly like z-scores. In the past, when we dealt with z-scores, we always talked about a sample size of 1. Is this one person's weight? What is the chances that this one person's weight is bigger than 70? What is the chances that this one tree grows less than 6 feet tall in its lifetime? And in those cases, the formula was x, the score, minus the mu, divided by the standard deviation. Now, you can always divide by 1. You can always divide by 1. And you could think of the 1 as the square root of 1. Well, with the central limit theorem, it becomes x minus mu over sigma over the square root of n. In fact, you can always think of z as being this. Now, what is going on with this additional part? Well, suppose you want to know the probability. So suppose I tell you that the mean of something, is 30. And I tell you we randomly select not one person to see if they're over 30 years old, okay? We're picking 20 people at random to see if they're at least 30 years old, see if they're over than 30. So you would have the square root of 30 in the bottom. We are no longer just asking a question about one person. Is one randomly pick one person, what's the probability they're bigger than 30? It's no longer that. We're picking more than one person. We're picking 250 people, and we're going to ask them, are they over 30? And this is the z-score to determine the probability that this is true or not. Okay, let's look at some examples. This should clear things up, I'm hoping. Okay, suppose that scores for the verbal portion of the SAT are normally distributed. So the scores for SATs are normally distributed. And the mean is 509, The mean is 509, and the standard deviation is 112. The standard deviation is 112. Okay. So now, suppose part A, you randomly select one person. You randomly select just one person. And the problem is, what is the probability that their score is at least 510? Find the probability that the score, with the C in it, is greater than 510. Okay, so what's going on is it's normally distributed. The mean is 509. 590 is to the right of 509, and we would love to know that area. Okay, and I had to go find my Z table. I'm sorry. Okay, so we want to know the probability that the score is greater than 590. So what we do is Z is equal to the score minus the mean divided by the standard deviation, which is 112, divided by the square root of the people that we are testing. One person. So basically, you don't even have to divide by 9. And you get 81 divided by 112. Let's see what that gives us. Okay, so 81 divided by 112 is 0.723. 0.723. And that's the number we look up on our famous table for z-scores. And remember, our z-scores only tell us the area up to a score. It will only tell us the area all the way up to 590. And when I look up 0.723, 0.72 is 7642. 7642, so the balance will be 2358. So the probability is just what I said, 2.2358. But now, what if we selected more than one person? What if we selected more than one person? Suppose if 16 people are selected. Okay, so now we are selecting 16 people. No longer one person, we select 16 people. So you randomly select 16 people. And you want the average score to be bigger than 590. So the big deal is here is that, oops, let's put down the marker. The big deal here is that n is no longer 1. We are selecting 16 people. So we divide by 16. And this number is going to be a little bit different. It's going to turn out to be 324. 324 divided by 112, which is about 3. It's just under 3. Let's see exactly what it is. Let's go to our trusty calculator. 324 divided by 112. You get 2.89. Okay, 2.89. Like I said, it's close to 3. 2.89. You go to your table. You look under 2.8 on the left column. You go across to 9, and you get 99.81. So now it's 99.81. But we want greater than 590. So we get a much smaller number. We get 0.0019. 0.0019. It went down. Okay, it's easier for one person to score well above the mean, but it's harder for 16 people to score well above the mean. The big difference here is we are selecting 16 people, so in the denominator we divide by the square root of 16, and that is called the central limit theorem, and that was part B. Because now we're randomly selecting 16 people. Let's try another problem or two. It's exactly what we've done before for z-scores, except now we're dividing by the square root of n in the bottom. Always divide by square root of n. So when n is 1, it won't mean anything. Okay, so suppose you are buying some soda. And you assume that the cans of soda are filled so that the actual amount has a mean, just has an average of 12 ounces. Okay, I mean it says right on the can 12 ounces. But come on, how can they fill each and every can with exactly 12 ounces? There's going to be some kind of a deviation there. And that standard deviation is, for argument's sake, 0.11 ounces. A little bit more than 1/10 of an ounce you may be cheated out of or you may benefit by. Now, what if you wanted to find the probability of exactly 12.19? So you randomly select 25 cans. Okay. Find the probability that the average is at least 12.19. Is at least 12.19 ounces. So we're looking for our answer here. In terms of our picture, 12 ounces is dead center. 12.19, of course, is more than 12, and we want at least. So I want to know the probability of being bigger than 12.19 if you select 25 cans. Instead of people, we're selecting cans. So z is equal to x minus mu over sigma divided by the square root of n, where n is 25. So the average that we want is 12.19. That's the score. And the mean is 12. And we're dividing by 0.11 divided by the square root of 25. And this is going to be 0.19 on top, and in the bottom, 11 over the square root of 25. And if you were to work this out, you would get very high number, actually. If you work this out, you get 8.63. You would get 8.63. This is well over 3, which is 8.63. Okay? Well, that would mean that that area is 0.999999 forever. It's going to be just a little bit more than 0. The answer will be just a little bit more than 0. 0.00000, I don't know how many, 1. It's not going to happen. If you select 25 cans, it's just not going to happen that the average is 12.19. It's too much. It won't happen. With 1 can, it probably would have been much different. But with 25 cans, it's not going to happen. Let's try another example. The only difference now is in the denominator, we divide by the square root of n, where n is the population that we are testing. You know, we want to know if these 25 people, if their average really is over whatever. Well, we do something about strobe lights. In aircraft, strobe light is designed so that the times between flashes are normally distributed. So in this case, when it says normally distributed, we don't worry whether n is big enough. Remember, if it's not normally distributed, then n must be at least 30. It's normally distributed with a mean of 3 seconds. So the mean is 3.0 seconds. And the standard deviation is 0.4. The standard deviation is 0.4 of a second. And you have a strobe light that goes on and off, and the mean average between flashes is 3 seconds. Find the probability that an individual time is greater than 4 seconds. That is, you just look at the millionth flash, or the time between the millionth and first flash, or between the 7th and 8th flash. What's the time in between? We want to know if it's greater than 4.0. The probability that in between 2 flashes is greater than 4 seconds. So in between 2 flashes is only 1 period of time. So n is not 2. Don't get caught up on that. You have a flash, you have another flash. What's the time in between? Is it more than, what's the probability it's more than 4 seconds? So there was only 1 period of time in between the 4 flashes. And that's what those 3 seconds mean. The average length in between 2 flashes is 3 seconds. Okay, so we know that z is x, which in our case is 4, minus the mean, which is 3, divided by the standard deviation. So this is 1 divided by a quarter, which I think is like 2.5, because this is 10 over 4. I just moved the decimals 1 place, and 10 over 4 is 2.5. So I look up 2.5. Now, with respect to our picture, here is the mean of 3 seconds, here is 4 seconds, and we want to know about bigger than 4. Excuse me. It turns out that for z equals 2.5, we get 9938. 9938. Remember, R only goes from the left up to the score. So to the right of the score will be 0.0062. The probability that one period of time between the flashes is more than 4 seconds is equal to 0.0062. The probability that between two flashes that the time is bigger than 4 seconds is 0.0062. Now, what if we were to change this problem? What if we were to say that we want to look at many of these flashes, not just one of them? Suppose we want to find a probability that the mean for 60 randomly selected times is greater than 4 seconds. So now n is 60. So now we have n is 60. And we want the average in between two flashes, the average time in between two flashes to be bigger than 4 seconds. Well, now what we do is we divide by the square root of 60. And everything to the right is going to now be different. In fact, the only real difference will be, and it's a big difference, is that instead of having 1 over 0.4, we're going to multiply that by the square root of 60. And we know what 1 over 0.4 is. We just did it. It's 2.5. Okay, no point in reinventing the wheel. 2.5 multiplied by 60 raised to the 0.5 is 19.36. 19.36, which is very rare. Okay, so this time we get 19.36, which of course is way over 3. So this distance here is going to be almost everything. Just be a little bit less than everything. So to the right, or greater than 4, will just be a little bit more than 0. So instead of being this number, it's going to be a little bit more than 0. 0.0000 for a while, 1, or maybe 4, or maybe 4.1. But it's going to be a long time. Now this notation 0 plus is not unusual notation. Whether or not your teacher and or book uses that, that's a whole nother story. But in my stat class, we'll use things like 1 minus. Actually, that's what I meant to put here. I should have said 100% minus. I meant to say 1 minus. It's a little bit less than 1. To be less than 4 is going to be very, very close to 1. A little bit less than 1. How little? Very little. Okay, let's try one more of these type problems. This is exactly these scores, except we divide by the square root of n. Always divide by the square root of n if you don't like two formulas. Just remember that if they say find the probability that one score is bigger than or less than or is in between these numbers, that n is 1. Suppose for some people their blood pressures are normally distributed with a mean of 114.8. So the mean blood pressure is 114.8. And the standard deviation is 13.1, with standard deviation of 13.1. If somebody is randomly selected, find the probability that their blood pressure is greater than 140. So, select one person. That's N. Find probability that blood pressure is greater than 140. So there's only one person selected. So Z is X minus mu over sigma, and we'll always say over the square root of N this time. The score in question is 140. The mean is 114.8. We divide by the standard deviation of 13.1 divided by the square root of 1. The rule for dividing by the square root of 1 is 1. The rule for dividing by 1 is don't bother. And what we get is 25.2 divided by 13.1. Little bit under 2. Let's see how much. Let's go to that trusty calculator of ours. Okay, so like I said, 25.2 divided by 13.1 is 1.92. 1.92. Make sure you round it off correctly. 1.92. So I look up 1.9 in the left column, and I go across the 2. 1.92 is 9726. This corresponds to 9726. Now, with respect to our picture, the mean is 114.8. We want to know about greater than 140. But the table I'm using only gives area up to a point, from the left up to a point. And that area is 0.9726. So the remaining area is 0.0274. And that's your answer, 0.0274. Of course, now the problem is going to be changed. We are now going to look at 4 people. Okay, now we're going to select 4 people. So it's no longer select one person. We're going to select 4 people. That means N is 4. That means we're dividing by the square root of 4. But the square root of 4 is 2. So this gets over 2. And if you work it out, it actually doubles. It'll be 3.84. Now, when you look at that number, 3.84 is no longer going to be 0.0274. If you want to go more than 3 standard deviations, it's going to be a little bit less than 1. It's going to be a little bit less than 1. So now the answer is going to be a little bit more than 1. Not like 2%, not 2.74%. It's going to be less than 1%. It's going to be less than a tenth of a percent. It's going to be 0.00003, something like that. So the probability is going to go down when we do 4 people. The biggest difference here with the central limit theorem is in the denominator, you divide by the square root of n. And for the record, if you don't like dividing by the square root of n, you have an alternative. Z is equal to x minus mu over sigma over the square root of n. Well, an expression always equals itself times 1. I'm going to write 1, so it equals itself times 1. And the way I'm going to write 1 is square root of n over the square root of n. The top is x minus mu times the square root of n, and the bottom is just sigma. To show you that more clearly, the square root of sigma over the square root of n, which is in this bracket, times the square root of n. Square root of n's cancel out, and you just get sigma. You need to think of this as making a mistake in your calculator. You have some number sigma, and by accident, you divide by the square root of n. And you forgot what that number was. Well, how do you retrieve it? You multiply back by the square root of n. That cancels out. And you just get sigma. Okay, so you can use this formula for z. Instead of putting the square root of n in the bottom, in the denominator of the denominator, you can put it in the numerator. So if that makes it easier for you, use that formula. Okay, that completes the section on central limit theorems.